Now, see, the next potential is pressure. So temperature and pressure basically they have ability to do something, right? So second potential is pressure potential. Pressure. See, pressure is represented by P, and it is also a kind of potential which determines the flow of mass. So pressure potential, a kind of potential which determines the flow of mass from high pressure region from high pressure region pressure to low pressure till the mechanical equilibrium, means till the pressure is not equal. Till the attainment of mechanical equilibrium. If at 2 point pressure is equal, then both points are said to be are under at mechanical equilibrium, right? See, again one point is missing here, that determines the net flow, right? So if you use here the word net flow, now your I mean statement is perfectly all right and always true. Now see, there is a possibility that some molecule may flow against gradient, against potential, but overall the net flow is always takes place from high pressure region to low pressure region, right? So see, suppose that if we have uh, system like this. Suppose that here some gas is there and here also some gas. Obviously, all the variables are there. Here pressure is P1 and here pressure is P2, and this time P1 is greater than P2. Now see, other variables are there. Temperature is there, volume is there, number of moles are there, but I am talking about only pressure here. Suppose that this the state of our system at t is equal to 0. T is equal to 0 means time 0. Now after opening this valve, so when this valve is open now, so what we observe, P1 is greater than P2, so some gas molecule will flow from here to here. flow from here to here. Few molecules also flow from here to here, but the net flow will takes place from here to here, right? Until the pressure is not equal. See, after some time, the pressure becomes equal in whole system. Now, initially it was a two component system. This system has two parts, but now this is a single system. So this will pressure of gas is equal at all points. So pressure gases, exert pressure in all directions, equal pressure, and it is independent of the shape of the container. So this P is definitely less than P1, but it is greater than P, right? This time. So gas will flow from high pressure. Net flow is from high pressure region to low pressure region until the pressure is not equal. So this is the property of pressure. Similarly, if we examine some other type of system, suppose that this is our system, and one partition is there, and suppose that this partition can move freely on this frame, and some gas is here and some gas is here. Let the t is equal to 0, means time t is equal to 0. This is the pressure P1, here the pressure is P2. So see, gas molecules are continuously striking with the wall of the container. Since this wall is movable, obviously here also they will strike, here also they will strike, but since these walls are the rigid, so there is no change. But if P1 is greater than P2, P1 is greater than P2, P2 molecules also striking with the wall, but relatively less number of molecules are striking. Since P1 is greater than P2, so this side more molecule will striking on the surface. So how gases, how exert pressure? Gases exert pressure by striking with the wall of the container. Once they will strike with the wall, there is a momentum transfer. Momentum transfer per unit time is force, and force per unit area is pressure. So as all we know that this is the basic formula of pressure, force per unit area, right? So this is the fundamental formula, and it is applicable everywhere. But remember, here this pressure is equal at all the wall of this container. It is not, you cannot say that here pressure is more and at this wall pressure is less, not like that. But in whole container, the total pressure is more than this part of the container. So this is the non-equilibrium condition. So if this gas molecule from this side, they were exerting more pressure on this, then what will happen? Your this partition will move towards right. This time there is no gas flow, but this partition moves from here to from left to right. This moves from left to right, and this partition will move till the pressure in the both the container, both the part of the container is not equal. So after some time, when equilibrium established, pressure of both the sides is equal. Right? So this partition will be under equilibrium. Suppose that here So the pressure means this time now the molecules which are striking with the wall from both the sides are equal, right? So okay, now pressure in this side and pressure in this side are equal. So this is the property of pressure, right? Hopefully all of you are getting. So how gas molecules exerts pressure? Gas molecules exert pressure by striking with the wall of the container. In the collision with the wall, there is a momentum transfer. Momentum transfer per unit time, force per unit area is pressure. So in this way, they will exert pressure. In a container, pressure is equal in all the direction in whole system. Suppose that if you have taken a irregular shaped container, so pressure is equal at all points, right? There is no change. This is not like other fluids like liquid, that when the surface area is less, then pressure is more. This is not like that, because here the mechanism is something different in case of gases. See, when you reduce the area, the number of molecules striking per unit area, that is also reduced, so accordingly pressure is reduced. Force is reduced, so accordingly pressure will reduce. So in this case, don't make the dependency of pressure on the surface area, right? So see, at the surface of Earth, we are, considering that one atmospheric pressure is there. This is the pressure of atmosphere, this air molecules. So it is equal at everybody. If you have a small size home or someone has big size home, this is not. You cannot argue like that, that small size home is there, so there is a more pressure, more atmospheric pressure is there. No, not like that, because they have different mechanism to exert the pressure. The pressure exerted by the gas molecules through the collision on the surface of the container. And if you reduce the surface area, number of molecules striking per unit area, they are also reduced, force will reduce, so accordingly pressure will reduce. Okay, so this is the most fundamental formula of the pressure, and all of you are basically knowing this measurement of pressure, how it is measured. So the very simple measurement of pressure is through mercury height. We are in a very simple manner, we are measuring the pressure, and also we have different units for pressure as well. So suppose that if we have taken here, this is a mercury, and take a tube, and this mercury will rise in this tube, mercury rise here in this tube. Suppose that this mercury rises up to here. So by this, from this surface, not from here, from this surface, let the height is h. So with this height of this mercury, we can evaluate the pressure of here atmospheric, in the atmosphere. See, P is equal to F by A. This is equal to, you can write rho G H. This is equation 2. Right, so rho is the density of the material. Here the density of this mercury is 13.6 basically grams per centimeter cube we are taking, and g is the acceleration due to the gravity, and at h is the vertical height. So see, this h is the vertical height. You cannot take this tube in the slanting manner. If you take slanting manner, then this is not, means same measurement, same calculation will not work. So h is the vertical height. So you can compare the atmospheric pressure in terms of height. You can calculate, right? So see what is the mechanism here. See, here gas molecules are there, and the gas molecules, they continuously striking at the surface of this mercury, and due to this striking there is a pressure exerted by the gas at this surface, and due to this pressure, this mercury will rise in the tube. Here this is vacuum, right? So here vacuum, and here this mercury will rise in this tube. So the pressure exerted by this P atmospheric, we can write here P atmospheric. So this pressure exerted by these gas molecules at the surface of this mercury, and due to this will rise. So there is a equilibrium. Forces are balanced here. So is there here there is equilibrium. So suppose that if this H is equal to, if H is equal to 760 mm, right? If H is equal to 760 mm, then what should be the pressure here? So see, P is equal to rho GH. We can use rho GH, and rho is 13.6 grams per centimeter cube, and G is 9.8 meter per second square, and this H is 760 mm. So this is equal to into 10 to the power minus 3 meters, right? So here this is meter, here this is grams, so this should be kilograms. So this we can write here 10 to the power minus 3 kilograms centimeter, and here this is meter. So it is what meter, 10 to the power 6. This we can write here kilogram into 10 to the power 6 meter minus 3. So if we multiply this whole, then we will get what? 101 101,325, right? So 101325 Newton meter square. Newton meter square. So this is 101325. It's okay. Here there are exact value 13.5 something like that. So it's okay, no problem. 101325 Newton meter square. Newton meter square is equal to, we can write 101325 Pascal. 101325, yes. So this is equal to, we can write 1.01325 into 10 to the power 3 to 5 5 Pascal, and this is, we can write 1.01325 bar, right? And this is equal to 1 atm also. 1 atm, right? So if you take this 1 atm, so 1 atm is equal to, you can write 1.01325 bar. See, there are so many units for this pressure, and all of you should be aware of all these units. And this is equal to 1.01325 into 10 to the power 5 Pascal. This is equal to 760 mm of mercury height vertical. This is equal to 760 torr, right? So these are the different units of pressure, and all of you should know all these units. Everybody should remember all these interconversions and all these units, right? So this is a very simple, you can say, instrument through which you can measure the pressure. Now I am going to show you some other systems for the measurement of pressure. See, these are also simple, not difficult, but now see, in this case, see how to evaluate the pressure. So suppose that here we have taken gas in this, there is a valve. Here the gas is there. So see, here gas is there. So this gas molecules, these gas molecules, they were striking on the surface of this liquid, mercury, basically. So here one pressure is exerted by this, gas molecules which we have taken here, and here the atmospheric pressure is there. So atmosphere, the air molecules, they will exert a pressure here. So atmospheric pressure is almost constant, but here I have written, I mean, it is given here 1 atm, P atm. So what is the pressure of this gas? See, from here to here, this arm and this arm, the mercury, what exerts pressure, that is cancelled out. See, this is the difference of mercury height in both the arms. So, this H height of mercury plus this atmospheric pressure, what atmosphere is exerting pressure on this surface, that is equal to the pressure of the gas. So, here see, this is very important, and you will, I mean, find such, I mean, relations uh, during the numericals, right? So here the pressure of the gas is equal to the pressure exerted by this ATM, I mean atmosphere, plus pressure exerted by this mercury, but not whole mercury, only due to the difference. That's why some mercury is here, so this is cancelled out. Okay, now this time, see here, this is the gas here. So these are the simple, actually instruments, you can say manometer, and they are open. In which container you want to measure the pressure, you can put this there, and then you can measure. Now this time, see, this R is in the lower side, means this pressure is more than this pressure basically. So this will push this mercury this side, and after all, at equilibrium, see, remember, every time you have to measure the pressure at equilibrium. Under non-equilibrium condition, there is no measurement of pressure, right? So in the beginning, when I have told you this pressure is a potential, see, pressure is a potential. So whenever the system is under equilibrium, only then you are going to measure the pressure, right? So when this movement of this mercury arm becomes stabilized, then we can say, okay, now we can measure the gas pressure of the gas. So this time the pressure of the gas is equal to this atmospheric pressure minus of this, because this time we can say that the pressure atm, atmospheric pressure, is equal to pressure of gas plus pressure due to this difference of mercury height, rho gh, right? Yani, I mean, pressure of gas is less than this atmospheric pressure. So here pressure of gas is more than P atmospheric pressure, and here pressure of gas is less than the atmospheric pressure, right? So this is these are called open arm, right? Barometer, open. These points are open. Now see, this is a closed arm. I mean this barometer. So this time, if you take gas here, so here gas is there. This gas molecule exerting the pressure at this surface by striking with the surface of this. Here the vacuum is there. So the pressure of the gas is totally balanced by the difference of this height of mercury. So pressure of gas is equal to the rho Gh. This time there is no, I mean, external pressure is here. Here this is vacuum. So this is the way of the measurement of what pressure of the gas by simple manometer, and this is very important. See, this is, that's why sometime we are talking about the absolute pressure of any system. So every time absolute pressure of any system is equal to the pressure of that system plus atmospheric pressure, right? So remember, absolute pressure, if we are talking about the absolute pressure, so absolute pressure is always equal to the pressure of the system plus atmosphere, because you know one atmospheric pressure is every time every matter is suffering from this one atmospheric pressure, right? So see here, 760 of mercury is equal to 1 atm. So if vertical column, if we replace this mercury with water, then how much this height will come? So it will come approximately 10 meters, right? It will come approximately 10 meters. So 10 meters of water column is equal to 76 centimeter of mercury column, right? So you can write, because you can compare density and G and H, and suppose that we have rho 1 H1 is equal to rho 2 H2, right? So what is the density of mercury? Density of mercury is 13.6 grams per centimeter cube into 76 centimeter of mercury height. This is equal to rho 2. Suppose that we can take 1 grams per centimeter cube for water. This is for water, and this is for mercury. So we can calculate H for this. So this grams cancel, centimeter cube. So 13.6 into 76. 13.6 into 76. So this is close to 1033.6. So H2 is equal to 1033.6 centimeter is equal to 10.33 meters. So we can say approximately 10 meters. Means if you want to measure here, sometimes someone may argue why you are taking this mercury. So taking mercury is, in some aspect it is disadvantageous, because this is something which is not good for health. But if you take water here, so the water column will rise 10 meters. So you have to arrange 10-meter water column. So that is also a difficult step. So 1 atm is equal to 10 meters of water column. 10 meters water column vertical height. So here you can write 1 atm is equal to 76 centimeter of mercury vertical height, and 10 meters of water vertical height. So suppose that if this is the surface of water or sea, suppose that this is the sea level, and this all these measurements were made at sea level. This is true at sea level and at 0 degree Celsius, right? Not at all temperature. So suppose that this is the sea level, and water is obviously filled here, and suppose that we are talking about an air bubble. Suppose that an air bubble is here, and this air bubble is at at 20 meters from the sea level. Suppose that this is 20 meters. from the sea level. So if it is asked, okay, what is the pressure inside this air bubble, pressure of gas inside this air bubble? So pressure of gas inside this air bubble from the sea level, which is at the depth of 20 meters, this is equal to pressure of this air which is filled here, pressure of air, or the pressure of here, pressure on this air bubble, pressure on this air bubble is equal to pressure of gas plus at 20 meters, 10 meters of water column is equal to 1 atm. So this is 20 meters, so 2 atm you have to add here. So the total pressure inside this gas bubble, that is equal to the actual pressure of this gas plus 2 atm. So we can say the absolute pressure here is the pressure of gas plus 2 atm. So this is the reason why when you are doing this deep sea diving, so every 10 meter, imagine every 10 meter when you are going into the deep, 1 atm pressure will increase. Per 10 meter, 1 atm added on your, lungs, right? Your lungs like a air bubble. So this is the reason why deep sea divers were having two cylinders. One is of oxygen and other is of nitrogen or inert gas, right? And you know what will happen if you take only oxygen cylinder, yeah, and if you are moving 40 meters down from the sea level, then what will happen? Your lungs will suffer, with high pressure of oxygen, and they gets damaged. So to maintain the partial pressure of oxygen 0.21 atm, it is mandatory to take some other gas and some automated regulation so that pressure can be maintained. Partial pressure of oxygen can be maintained in your lungs. So this is the reason why we are, taking another cylinder of nitrogen or helium gas. It is better to take helium, not nitrogen, because nitrogen will cause, when it will dissolve in your blood, it will cause some illusion, right? And also when you come out, then it will deabsorb, and this will cause the pain in your veins, right? Well, see, let's do some problems based on this. Suppose that question is given: find the approximate mass, find the approx mass of atmosphere of atmosphere around the earth, around the earth, and radius of earth, radius of earth is given 6370, 6370 kilometers. It is given, right? Suppose that this question is given. So assume that Earth is, spherical, right? So radius is given. So we can use this formula Basic formula P is equal to F by A. So force is equal to, you can say, M into G by A. A is area, but in this case, you see, this is spherical, so you can take surface area. Surface area. So mass is equal to, you can write mass of air, basically mass of air is equal to pressure of air into 4 pi r square. R is the radius of that sphere, I mean earth, divided by G. So if you put all these values in a proper unit, you will get the, I mean, correct answer. For this, what is the pressure at the earth atmosphere, pressure of the atmosphere on the surface of the earth? That is 1 atm. So we can write here 1.01325 into 10 to the power 5 Newton per meter square into 4 into 3.14, you can take, into R 6370 into 10 to the power 3 meters square, whole divided by G, 9.8 meter per second square. So you will get the mass of air 5.7, 5.27, basically 5.27 into 10 to the power 18 kilogram. See what a huge value is this, right? This is the answer. So if you see here, this is a huge value, and now you can, if you are able to, find out your surface area, then you can count how much this mass of atmosphere is present on you, or at your home, or at any object. This is the overall total mass of atmosphere at the surface of earth. One more important point is that, see, this pressure of atmosphere, see, this also changes with the altitude, right? So pressure in laboratory condition, under laboratory, when you take a small container, then in that container there is no significant difference in the magnitude of pressure at the bottom, at the top. But in under atmospheric pressure condition, the pressure changes with the altitude. So a variation of pressure with height is given by this formula. Pressure at any height h is equal to P naught. P naught is the pressure at sea level, e to the power minus m g h by r t. This equation, where pH is the pressure at height h, P naught the pressure at sea level. Sea level. M is the molar mass of air, and the unit should be in kilograms per mole, right? And molar mass of air, it is what, 29. All of you are knowing that average molar mass of air is 29 grams per mole, right? M is the molar mass. G, all of you are knowing. H is the height. Height. Obviously, you should take the unit meter. In meters, always put G in meter per second square. R is the, gas constant, value of which you should take 8.314 joules per mole per degree Kelvin. So all the units in the SI system, and T is the temperature at Kelvin scale. Temperature at Kelvin scale. Kelvin scale. So this is the formula. By using this formula, you can calculate the pressure of this atmosphere at any height h, right? So suppose that the question is given to you, and this you should do as a homework. All the informations are here. So as a homework, you should write, calculate the pressure, uh, calculate the height, calculate the height at which the pressure becomes half of becomes half of its pressure at sea level. Sea level, right? So calculate the height at which the atmospheric pressure becomes half of its atmospheric pressure at sea level, right? At sea level. Temperature, you can take 25 degrees Celsius. Temperature 25 °C. So all of you should calculate. See here, P and P naught, whatever unit you are taking at sea level and at height h, that should be the same. If you are taking here ATM, then you have to take here ATM, so this will cancel out. So in this equation, when this type of equation you have, there is no meaning of unit, because here there is no unit of this will be exactly cancelled by unit of this, and unit of this is cancelled by this, right? So now you can take here both the same unit. Don't take here, this is in atmosphere and this is in Pascal. You should take both the pressure, at sea level as well as at height h, that is in the same unit. Okay, so try to calculate this.